Good morning, everyone. My name's Chris Armstrong, Acting Chief Scientist and Engineer. It's great to see everyone here today. I'd like to start by acknowledging the traditional owners of the land, the Gadigal people of the Eora Nation, and pay respects to their elders past and present and future. Today's presenter, Veena Sahajwalla, grew up in one of the most densely populated cities in the world, Mumbai. There, she experienced firsthand the massive amounts of waste which a large society can produce, and has made it something of a personal mission to find ways to reduce its environmental and social impact. Many of you will know Veena from her work on green steel, using waste tyres to toughen steel, which has recycled millions of tyres from vehicles as a partial replacement for coke. But Veena has not confined herself to tyres. Society's unstoppable desire for the latest and best technology means that the world's waste mountains are increasingly dominated by discarded computing and electronic equipment. And Veena is therefore developing innovative techniques to combat electronics waste. As director of the UNSW Sydney's Centre for Sustainable Materials Research and Technology, also known as the SMART Centre. The centre is not only reducing the environmental harm from the waste is causing, but also pioneering ways to recycle useful elements like carbon, silicon and metals from the waste, and the materials which industry would otherwise have to source anew. Veena has unsurprisingly received many national and international accolades for her work. She was recently appointed as a Fellow of the Australian Academy of Science, so congratulations. She's an ARC Laureate Fellow. She's received prestigious Jubilee Professorship from the Indian Academy of Sciences in 2017. And she received the New South Wales Science and Engineering Award in 2008 for engineering. Please join me in welcoming Scientia Professor Veena Sahajwalla, FAA, as she presents Green Microfactories, Products from Waste.
Thank you, Chris, for that very kind introduction, and thank you so much for having me here today. It's indeed such a privilege and an honor to be speaking in this amazing place. As you heard from Chris, I was born in Mumbai, and for me, my parents live there, and it is in a way a place that has been an inspiration for me growing up in a place like Mumbai, where of course you see all elements of life coming together. And so to some extent, you know, when I look at the kind of work that we do at UNSW, and we look at the privilege that we have to be able to do some incredibly fantastic work, supported by the university, supported of course through ARC and our industry partners. But the fact that everyone is so passionate about not just the science and doing world-leading science and creating impact through that scientific work, but also equally importantly, looking at what that science means for humanity. So does it mean that we're actually going to help people in so many disadvantaged communities globally as a result of this science? Are we going to be able to deliver this work in a way that it adds value to everybody on this planet? So it's really about recognizing how all of this work that we do has got a role to play in creating impact, whether you're in India, in Africa, or in Australia. And for me, that's the real privilege, to be standing here and to be talking about work that I'm passionate about, but I'm also so excited about the fact that we've got support from our university, from our industry partners, to be able to do this work in a way that allows us to challenge a lot of the conventional thinking. And so in a way, when we think about recycling, the big picture here is very much about the fact that we need to be able to think about game-changing solutions, because lying in the core of all of our end-of-life products, whether they're electronic products, glass, plastics, metallics, what have you, are valuable elements that, of course, we just can't think of it in a traditional sense of saying, well, let's just recycle it because we have to, it's the right thing to do, or, I really don't want to pollute the environment. All of those are good reasons. But the other hard-nosed scientific economic question can be asked at the same time, which is if all of these elements that we have already mined out of the ground, for example, our copper and cobalt and lithium, and the list goes on, why are we not seeing it from the context of how do we bring it back to life again in a way that doesn't do harm to our environment, in a way that doesn't do harm to those disadvantaged communities globally who actually may not even necessarily realize that burning electronic waste and burning plastics can potentially do a lot of harm to their personal health. So it's all of those questions where our role as researchers should be very much about developing that holistic understanding and, of course, as much as possible, creating technological solutions that are indeed affordable, that are sustainable. It's no point just saying, here is a fabulous billion-dollar smelter, now off you go and put that on where you are and all the problems are solved. Of course not. What you have to be able to do is develop technologies that are fit for purpose. So first off, it's important to recognize that not everything has to fit within the principles of economies of scale. That is one way to look at how business can deliver solutions. But if we're smart and we develop value-added materials, then we can actually start to think about economies of purpose. And I think that's really what I want you to start to think a little bit more about. What these types of end-of-life waste resources offer us the opportunity to do is exactly that. So when you want to actually regenerate materials and elements like lithium and cobalt and nickel and all of these valuable elements that, of course, as you all know, are present in our electronic devices and batteries and so on, we should be looking at how we can regenerate those types of elements in a way that actually continues to add value. So therefore, what that then means is we are starting on this journey, which we should think about it as a regenerative economy. It's not just about, yes, it's nice to have a green economy, but I think more importantly, it's equally relevant in our society today that we can develop technologies that are not just doing social good, that are not just preventing harm to the environment, but if we can indeed create economic value and create technologies and create solutions that actually are sustainable in the long term from an economic point of view, in addition to all of those other points that we've talked about, then of course we know for sure that in the longer term we're going to create jobs and deliver economic benefits to those communities. And I think that's really the critical challenge. It's not just about working with business partners who can afford to spend millions and millions of dollars on new technologies. And that's what we have to do anyway. We have to prove that the science works on all scales. And I think that's where the challenge is. It's not good enough to say, well, I'm just going to develop a technology that depends upon, many, many tons of this material being produced on a mass scale. What if that's not viable? What if you're in a remote disadvantaged community where waste is still collecting, because of course we still have to deal with our phones and computers and waste glass and plastics? What if we can't actually set up these types of expensive infrastructure? So the point really comes down to, can we actually develop microfactories that allow us to deliver these types of solutions and create different types of value-added outputs, whether they're utilized in the local community or whether they are so valuable that they are potentially part of a global supply chain. So could we create valuable materials that we could then contribute into the global supply chain? And why not? We don't have to always look at ourselves as, oh, we don't produce this finished product, we don't make cars, or we don't make our phones and TVs and so on, but we can make valuable materials out of these types of end-of-life products that then can contribute to a global economy, that global value chain. And that's the important thing to look at. It's how we actually create that value on a local scale that then contributes into a global economy. And I think unless and until we think about it in that way, we're not going to be shifting ourselves away from a traditional mindset of recycling. We're not going to be shifting ourselves away from that traditional mindset of how traditional large smelters are the only way to do business. They are definitely not the only way to do business, particularly when you're talking about valuable elements that present themselves in our electronic resources. And this is where, of course, I'd like to acknowledge the fact that at our university, we do have solutions that cover the full spectrum, from the fundamental science, starting at the molecular level and the transformation of how we've shown that using waste tires in the process of making steel delivers valuable molecules of hydrogen into the process of making steel that then allows us to tap into that carbon and hydrogen, not coming from necessarily always from coal and coke, but rather coming from these types of end-of-life materials like tires that then allow us to not just recycle those tires, but actually allows us to create a far more efficient steelmaking process. And I think that's the way we saw the whole challenge, that if we were to look at it from the lens of a steelmaker, they could very well ask the question, why should we recycle tires? What's in it for us? And that's where we started our journey, even though we knew that the underpinning drivers for us are about the environment, are about the social impact. But if you were to introduce tires into a steelmaking furnace, what is it actually going to do? And so some of the work that we've done has shown that in our world's first steelmaking technologies, where green steel now is commercialized, not just in Australia, but indeed across different countries in the world, we've actually shown that we've successfully recycled millions and millions of tires in the process of steelmaking. The benefits that emerge are obvious. What we have shown is we've reduced the carbon footprint, we've reduced electricity consumption. It's a no-brainer. Why would someone say no to it? And this is before the argument of the fact that we can indeed recycle waste resources. And that's where we want to get to with our microfactories. We want to be able to generate elements and materials and products out of the full spectrum of end-of-life products that we as a society, not just here in Australia, but globally produce. What you can see there on your screen is the whole mixture of those everyday things that we all use. But where do these types of electronic materials and, of course, our polymers and all of these materials come from? We know that, but can we actually regenerate and deliver new solutions? Can we actually generate products for the built environment, for the steel industry, for indeed producing high-value carbons, indeed producing products that are used by our utilities like Sydney Water, producing rare earths, and producing materials like plastic filaments, which of course our e-waste recycler is now looking to produce out of electronic waste plastics. So those are just some simple examples of what has been possible in partnership with industry. We want to, of course, acknowledge in there that without the fundamental science, without the research being funded through ARC, for example, none of this would even see the light of day. So it is absolutely important that the credible science continues to happen and continues to be published on a world-leading stage. We want to, of course, show to our industry partners that we're not just talking about that science piece, but we're also talking about that entire journey that enables us to work together in partnership. And this is where, for us, it is actually really, really nice to be able to see that our industry partners are interested in both the science. They love the science, but they also love the engineering, the technology. And of course, as businesses, you have to be economically viable in the long term. So the economic plan has to add up. What is that plan for them and why are they doing it? For a simple reason. Let me tell you an example of materials like carbon, high value, highly crystalline carbon that go in the formation of electrodes. These types of materials over the last 1 year have doubled and tripled and quadrupled in their prices. They used to be worth something like $2,000 a ton, these types of electrodes. They are now worth a whole lot more. So if I'm a steelmaker and I need to depend on carbon electrodes in my furnace, well, guess what? The cost of doing business has suddenly gone up. So it's not just about us telling the steelmaker, well, it would be nice if you could regenerate some carbon from tires, for example. Right now, it has actually shown a pathway to our steelmaking partner that this is now becoming an economic imperative, that if they, unless and until they can find new alternative strategies to generate carbon from these types of waste resources, they're going to have to continue to pay increasing cost of carbon electrodes. And that's just a simple example of how things have turned around in a global context. We don't want to be waiting till that crisis point hits us so hard that businesses have to shut down. We've got to be strategic in our long-term thinking. And this is where, of course, working with industries to be able to trial and test new ideas is also critical. And therefore, working together on the journey of commercialization is important. I do want to acknowledge both of our DVCs, DVC Research and Enterprise from UNSW, who are here today, who have both been absolutely strong supporters of the research and the work that we do in our industry partnerships. Because unless and until we all believe in those values, we're not going to see change happening. And we need change to happen at a really, really rapid pace. No doubt you've heard in the media around all of that crisis around how China has imposed new guidelines around the waste resources like plastics that they will and won't take from places like Australia. So certainly from our context, it is an important challenge that we all face as a community. So is it good enough to say that we just have to carry on doing reduce, reuse, recycle? Of course. Where we can do it, we should. We should look at how we might be able to transform really good quality plastics like our PET bottles and so on into new materials because they're worth good money. Even the recycled pellets that you would make out of nice clean PET is worth a lot of money. Of course you would keep doing that. But what happens when you've got the more complex, hard plastics, mixed plastics? Well, guess what? China has put that restriction on us right now. They will not tolerate contaminants up to the point where we're sitting there scratching our heads going, oh, what do we do now? Do we just go back and say, let's put on another new machine, and they keep making those tolerances more and more strict? Or do we sit back and go, wait a minute, there are a whole lot of other avenues for us to be really smart about it. And this is where the example of producing filaments, plastic filaments, from 100% recycled e-waste plastics is one example of how a solution can actually be a game changer. Because guess what? These plastic filaments then can be fed into 3D printing. And you might say, that's great. What does that mean to businesses, to SMEs, to manufacturers? It means that they can actually run 3D printing by depending on resources that can be locally generated that are affordable. It allows them to do prototyping. It allows them to generate new products. So effectively, it pushes along that economy to, in fact, give us a whole lot of new solutions that might not have been considered affordable in the past. So it's really around waste to value. And here's an example of our industry partners' factory that you'll see. Of course, fabulous work by our industry partner, TES, in looking at the whole of life of products. So where you can actually refurbish these types of electronic goods, of course, you would refurb them, you would on-sell them, and that's part of the whole economic evaluation. But on the other hand, we also have to be mindful. You don't want to have these types of waste resources ending up in places like India and Africa where the products don't work and all people end up doing is burning plastics to be able to get to metals like copper. What you want is, indeed, if we are creating a value chain, then developing sustainable and affordable technology should be part of our thinking. And indeed, our industry partner located in Sydney is looking at generating these types of filaments as part of the waste plastics that they generate. But of course, what you see on that video there are waste that, of course, you and I produce out of our homes and our offices. When we, of course, end up throwing away our old computers and TVs and so on, guess what? This is where it ends up. Now, we can either take that responsibility and see our responsibility as creating new science and new innovation that enables businesses globally to adopt some of this new science. So that's where part of our journey last year in looking at how this is actually happening at the ground level in places like India was really, really important to be able to see that there are amazing small businesses that can actually do so much more. So we can empower local businesses to do that. Of course, I don't need to tell you the whole spectrum of electronic waste that we're generating globally, worldwide, massive opportunity. Okay, where does Australia sit in that context? Where Australia sits, if you look at this in terms of the amount of e-waste that we're generating per capita, really only after Americans. So if you can imagine that we're producing about 25 kilograms per capita, and you've got Americans producing about 30 kilograms, we're not too far behind in the scheme of things. So if we're actually producing so much per capita, of course, No surprise there. We all love our devices and we all love our phones, multiple phones and TVs and computers and so on. Can we not be part of the solution that in fact puts us in a pioneering and a leading role globally? And that's really what we're doing at UNSW. Again, why? UNEP has put out numbers, billions of dollars worth of resources that are embedded in these types of materials, end-of-life products. So of course, we should be looking at the possibility of that transformation. So what this slide is really just showing you is the journey going from those waste plastics, coming from e-waste, producing filaments, and moving on and producing products like spectacle frames. We've got, again, partnership with consumers, manufacturers like Dresden, who produce spectacle frames, looking at the possibility of using variety of different types of waste plastics as part of their manufacturing journey. So again, the ethics and the values of this company line up perfectly with what we believe in at UNSW, that if we can put that science to good use, where it not only delivers a product that is affordable in Australia, but it's also affordable in places like India. So how do we actually do that? The way we do that is we look at the input feedstock. And in this particular case, the frames that are made out of plastics enable us to use a variety of locally available waste resources in manufacturing. So indeed, what we do then, 3D printing is now becoming more and more standard, more and more affordable. We can then use those filaments and feed them as part of these types of manufacturing technologies, which then can be done in a microfactory. Again, very, very practical, relevant challenges that small businesses face. So I was visiting a small window manufacturer where the frames were being made out of PVC. And for this guy, even though it was only $70 a week, but that's $70 a week in cost of disposal, right? But you can imagine in contrast, if what he was able to do is use that waste plastic to convert that into filament, to 3D print the products that he actually needs in his own business, he's not only converted a negative into a positive for himself, but he's actually enabled a whole new way of manufacturing that he can then be empowered to inspire the others around his community to be able to take the waste plastics that they have. So of course, that's the journey of plastics. Metallics, of course, we all know, lots and lots of valuable copper and gold and precious metals are available to us in electronic devices. So can we actually transform those circuit boards into metals? So in this particular instance, you can see right there, we're transforming circuit boards that allow us to create those metallic alloys in that one step. So from our point of view, if there are businesses that are already processing e-waste, already generating the resource, that circuit boards, why do we need to send that away elsewhere to other parts of the world? Why can't we actually create those metallic alloys, copper alloys, tin alloys, and of course, don't forget gold, and you can enrich a lot of these types of metallic alloys, and you can customize and tailor those alloys that are fit for purpose. And I think that's really the key here. It's not about having one big smelter that produces hundreds of thousands of tons of copper and copper alloys, but it's about saying, if I've got a whole series of distributed and decentralized manufacturing capability, I can actually be quite agile and flexible in looking at different types of input feedstock, because that's the whole point about waste. It's not one nice uniform thing day in and day out. It's about looking at that diversity of what comes in, and of course using our science to in fact tailor the operating conditions to deliver those types of expensive alloys. So that's really what the Smart Center's vision is, that we want to be able to create these types of distributed manufacturing solutions. And of course, it's a no-brainer then. If you can actually do that, you can then create local jobs. You can actually enable new economies to flourish in so many different parts of the world. But the other all-important thing, it actually minimizes transportation of waste from point A to point B. Why would we want to do that if you can possibly contain waste within a travel distance of about 100 kilometers, 200 kilometers to enable a localized sharing of waste resources and have various people, various industries in different communities reasonably close to each other processing different input feedstocks. So someone could be responsible for glass and someone for different plastics and metallics. That then allows all of us to actually allow each other to flourish. And that's what's missing right now, is that we're not seeing the bigger picture in terms of the disposal of these types of products. We're not seeing the fact that, in our electronic devices, we've got everything. We've got metallics, plastics, glass. We can't just think of it as one big recycling facility. We've got to think of it as a variety of different types of new opportunities. So this is where, of course, for us at the Smart Center at UNSW, it's very much about delivering these types of Australian-based solutions not only to Australia, but of course, as you can imagine, this is a global challenge. This allows us to make a difference to that whole important question about where are these materials going to come from. So we can sit there and ask those questions around rare earths and copper and so on. Are we always going to depend on mining these out of the ground, or are we looking at what resources we have in our hands globally and converting those into valuable materials? So here's an example of something simple that we've all faced. Windscreen glass in our cars. What does that contain? Why is that so important? This is not your stock standard glass that you can say, just send it off to a glass smelter and that'll be fine. This actually is a laminated safety glass in our cars to keep us safe. It's got glass and plastics, and of course, you want to be able to create and design these products. So you can't just say, oh, well, why don't we design things differently? Of course, that's an important question. You've got to think about the design up front, and that's an all-important question. But in case like a product where you've got an automotive glass designed to keep us safe, you can't then say, well, let's not do that. We have to do that because it's safety first in this case. What happens now is you cannot then feed that back into a normal glass smelting furnace. So therefore, what you have to do is start to think about a whole nother solution. That combination of glass and plastics that you're seeing there with a lot of residual ferrous and steel materials, what we have basically shown is we've been able to convert those types of materials into what you see on the right-hand side there for you, ferrosilicon alloys, where the silicon comes from silica that's present in these glass resources. So the ability to transform that into these expensive alloys is important, because you might say, well, who cares? Who cares? Because the world still needs ferrosilicon alloys. And of course, these are expensive alloys. They might cost you something like $1,200, $1,300 a ton. And of course, not everyone can manufacture these. But if you could do it locally, you could be supplying that to various people who need to produce specialty steels that contain high levels of silicon, for instance. This, of course, as you can imagine, what you're looking at is a stockpile of tires. Yay! Thanks, Dick. Well, I guess, this is the point, isn't it? You can sort of sit back and go, well, it's harmless, it's out there, no one can see it, so it's out of sight, out of mind. The realities are that, of course, these things can catch fire. They're not exactly harmless. They can catch fire and they can cause a lot of harm to our environment and to our communities. And of course, that's why we have laws about how much you can stockpile, waste that you can stockpile in Australia. Why? Because, of course, you don't want combustible materials like plastics and tires to catch fire. So what do you do? And of course, you might have noticed that there are 3 guys walking alongside that massive stockpile. So you can just see it is a global problem. And this is where, of course, our polymer injection technology in partnership with OneSteel has indeed solved the problem to some extent. We are, of course, on that journey and continue to be on that journey in terms of globalization of this technology. But it had to start somewhere. And it had to start somewhere. It started with OneSteel. It started right here in Sydney, which meant that we needed to have cooperation of all authorities. New South Wales government, where EPA comes in, looks at what you're doing. You had to have ARC funding. You had to have university. You had to have labs. It's all of that ecosystem that allowed us to get to this point where we are today with recycling these tires in the process of making steel. So the fact that polymer injection technology is now considered standard operating practice at OneSteel in Sydney and Melbourne, and of course in other parts of the world, in UK, in South Korea, just goes to show that it can be done. That's a difficult, challenging environment to work in. when you've got steel makers who are, of course, going to be worried about safety, of course, going to be worried about the quality of steel, they're, of course, going to be worried about emissions. All of those challenges have to be looked at in a holistic manner when you're doing the science, and not just look at it as an afterthought later on. So we've been able to do this, and of course, similarly, various technologies that have shown in different parts of the world that it works. Why does it work? What those series of rows are showing you, whether it's comparison with 100% coke and a whole range of different types of polymers, high-density polyethylene, rubber, and so on, is that by the time it has spent 5-10 minutes inside the furnace, you can see from that small lab scale measurement that we did way back when we first started on this journey, that the basic liquid that you're seeing on the right-hand side compared to coke, all the other polymers actually showed a far better performance, which you can see from the increased volume that we're seeing inside the labs. Why was that so important? It actually said to us that not only were we releasing gases like hydrogen, which of course reduced the need for carbon in these processes, that hydrogen was actually carrying out that reduction reaction. We were generating more and more metallic output as a result of the fact that the hydrogen molecules being liberated from those polymers at those temperatures enabled the reactions to take place in a highly controlled manner. So that was the key there. You know, we know that there's hydrogen present in a lot of these polymers. So why does it matter in this case? It matters because you've got to have the right controls so that the right chemical reaction takes place in the right time. And that's really the essence of this. And either way, of course, it can do a lot of harm. So it's about recognizing that these technologies are not easy. And indeed, I'll skip through some of these videos in the interest of time, but what this is just to give you a little bit of a snapshot. When we started our journey way back with our industry partners, it was actually understood that coal and coke were standard materials that were used in these furnaces. And even though you ask the industry partners around, you know, this is not really working well, and they recognize that, well, what are the alternatives? Well, the alternatives, the answer was always, well, it's coal A and coal B and coal C, right? So, I mean, in a way, we were sort of stuck within that paradigm that said these are the traditional materials that we always use. This is how steel makers do it in electric arc furnace steelmaking. What you're seeing there is liquid slag. This is a furnace in our labs, 1550 degrees Celsius, where that liquid slag contains iron oxide. The base that you're seeing there is coke that delivers carbon. And of course, what you see from that reaction is that it's happening, it's nice and slow, and it converts that oxide into a metallic form, and that's really what you want to achieve. Now, in contrast, when we started doing this work, we started using waste rubber tires and plastics, what was pretty obvious, and I'll skip that now and move on to the next one, when we introduce exactly the same system, but now, if you look at the slag and compare it to what you saw earlier, what you'll see in that liquid slag phase, which contains iron oxide, is that that chemical reaction as a result of generation of hydrogen, which is liberated from that molecular structure, allows us to therefore carry out those reactions, and not only carry them out fast and efficiently, because you can just see from the visual examination of that video that that reaction is enabling gas bubbles to be generated inside at those temperatures. Not only that, these gas bubbles are retained inside the liquid slag that allow these reactions to take place. So from that context, it had suddenly now become a material that was seen as a negative, a waste, whereas in this context, it was actually performing better than traditional materials. And of course, the reason why industry would have never even considered it is because it was branded and labeled as a waste. No one had probably understood that from the point of view of this reaction at 1550 degrees Celsius, the speed at which we achieve outcomes has been fantastic. So for us, that productivity gain is also critical. So if you want to be able to produce more materials, more steel, get more output from that same furnace, this is the way to do it. These are the advantages for a steelmaker. Yes, it's nice to be able to recycle tires and plastics in this journey. We want to, of course, look at what else can we do with this situation. It's not just about saying, well, right now we're using a combination of some amount of coke, and yes, the change might come, but Could we ever imagine a situation where we completely eliminate the need for coal and coke in these types of processes? And the answer is yes. This is where the science is happening at UNSW. We are moving forward in terms of the next generation of these types of electric arc furnace steelmaking technologies that can potentially see the complete elimination of the need for these types of traditional coal and coke-based resources. How do we do that? How do we know that we're going to be able to source our carbon materials, the solid carbon? Because remember, the reason why we're using coal and coke is for that solid carbon. The polymers are fantastic. They deliver those gases that we need. What this is just showing you is that by analyzing a lot of the data that we get out of these videos, we get the data, we analyze them in the lab, we've actually shown that ability to take this type of information from the lab and actually demonstrate the benefits in an actual steelmaking environment is possible. So that translation has to be done in a really clever way. Of course, our furnaces are small. Of course, what we're doing is on a much smaller scale. But what you can see there are the two tables of implementation in both Sydney and Melbourne. And you can see that compared to the standard material coke, till we came along and we introduced rubber and polymeric materials like LDPE and HDPE and so on, you can see the reduction in that electrical energy consumption in that steelmaking furnace. We were reducing that by 10 to 20 kilowatt hours per ton of steel. This is per ton of steel. We also were able to reduce that carbon consumption in that process. So for us, in a way, the holy grail with a lot of these types of manufacturing technologies is that can you ever imagine it becoming completely a renewable material? Can you ever imagine that all of the materials that we want to generate and regenerate, can we actually do that without depending on a lot of traditional materials like coal and coke? And that's really where we want to get to. Can we actually see that maybe we don't need to mine quartz out of the ground if we want silica? Should we be able to tap into waste glass? And of course, if you ask anyone, I'm sure in New South Wales government, the answer will be yes, because we're facing this crisis right now where we have a lot of waste glass and plastics that we cannot simply send away to China. So it's about asking those questions where could the possibility of combining waste glass and plastics give us potentially the opportunity to create these types of expensive metallic alloys. And that's really what steel is. It's an alloy at the very basic level of iron and carbon. And then if you add on to that all the specialty steels, then you start to think about all of the alloying additives that you need, whether it's chromium, manganese, and so on. So can we actually imagine creating these highly specialized alloys in a microfactory? You don't have to necessarily produce always the finished product, but you can regenerate the expensive input materials. So the expensive alloying additives can be regenerated through these types of microfactories because the additives are actually only small quantities. You only need a few percentages of these types of alloying additives to make a material better and stronger and so on and so forth. So for us, it's about questioning where is that value. If you want to be able to generate these types of expensive alloying additives like silicon and manganese and so on, can be done out of the waste resources through the technology that we have right now. And therefore, let's not throw away these types of resources. We've also got some of the work that we're doing right now in looking at some of the other oxides and carbides and nitrides, moving more and more into the realm of some of these really, really expensive materials, like, for instance, in this case, with rare earths. No doubt you've heard about them. And again, very important materials in manufacturing so many of our electronic devices. As we look at our dependency on electronics as a whole, this is not going to go away, but we can regenerate these types of materials out of our waste resource. So an example here of what we've done, we've taken magnets, which are present in our hard drives. We've then effectively shown that by using the carbon that we generated from tires, we can indeed convert that magnet, which contains iron and neodymium, into two separate phases. And that's the important thing. How do you actually isolate these types of rare earths from everything else that it's present in? You look at the environment. In a magnet, it's got there's a lot of iron that's present. How do you isolate that iron away from the rare earth oxide? That's where this technology has been proven scientifically it can be done. Why have we done that? And why have we achieved that? Because we didn't just get ourselves looking at the rare earths. We actually looked at the environment. We said, can we actually isolate that iron? Because iron's easier to deal with. Can we actually melt that liquid phase out at a temperature that is low enough? So how do you make iron melt at a low temperature? You saturate that with carbon, you drop its melting point, separate it out, and that's exactly what you're seeing there. So you see in that diagram there, you've got distinct two phases, and that all started out as one magnet. You see the bright shiny phase is the metallic iron that is nicely separated out. Now remember, even that iron is a valuable material. And of course, what you have there is the dark gray, which is the rare earth oxide. So you can actually start to show that it is possible to do these types of things. And of course, right now in Australia, we do put a lot of effort in actually separating out these hard drives. So we put in all of that work, but we just don't take it to that next step. And this is where microfactories can be so transformative in what we can achieve. I've talked about glass, but in this particular instance, again, the more complex glasses that are there in our e-waste are interesting examples of how we can indeed convert them into expensive ceramic materials that have got fantastic thermochemical properties. They are really good as photocatalytic materials, producing silicon carbide, silicon nitride, and all of these materials are worth a lot of money. So that's really what it comes down to. Why would a microfactory want to do this? Because of the fact that these types of materials cost thousands of dollars a ton in the marketplace. You can go and look up prices of these materials. You don't have to produce a shipload full of these materials. You actually can produce small quantities in a microfactory, because remember, if they are used in small quantities in various devices, in various applications, you can actually regenerate these materials on a smaller scale and actually export that out to places where manufacturing might be taking place, even if you don't have manufacturing of the finished product here. But you can imagine a day should come when people should start thinking about, if I really need batteries for energy storage, why don't I actually make these electrodes myself? Why am I dependent on somebody else to give me the whole battery? Let me at least start to make the electrodes and supply that. Once you start to produce electrodes, and you say, wait a minute, it's not too hard to produce the whole battery. Why can't I produce that myself? So part of that discussion is really around starting the journey somewhere. And this is why I use that example of carbon, where carbon electrodes are important components. And it's about starting to produce these value-added components that we need in our society. So here are some examples of what these materials actually look like. And of course, important, very important to produce these nanostructured materials in an affordable manner. Why? Because if they become more and more expensive as feedstocks, guess what? The finished products are going to become, again, more and more expensive. So just like the journey I was telling you earlier about the electrodes becoming so much more expensive, carbon electrodes for the steel maker, now you start to think about a lot of these types of materials that right now seem affordable, are devices, are materials that seem affordable, but when they actually start to actually become more and more expensive, it's going to challenge our ability to afford some of these types of devices. So we want to be able to make sure that if we're going to be part of this value chain, we need to be able to regenerate some of these materials ourselves. So again, some examples of these types of nanostructured materials. Again, fabulous thermochemical materials. They are ceramics, they are corrosion resistant, fantastic properties, physically really, really stable, can actually operate at very high temperatures. So you've got all of these types of fabulous properties in these. It's a question of, can we actually make these types of nanostructured materials and on-sell them to manufacturers? And the short answer is yes, that's what the science is starting to show. Another small example of your everyday stuff that I'm sure you've seen when you're actually changing your cartridges, your printer cartridges at home in your printer. You can imagine that if all of those printer cartridges were indeed just being shipped away or put into landfill, or and you were worried about it, and you were thinking, well, gee, this is really not possible because it's just this horrible contaminated mix. Well, actually, that black powder in there is rich in iron oxide. About a third of that is iron oxide. You've got all the plastics that's there in the product itself. So what we're doing with our industry partner here is showing that it is indeed possible to take, again, that combination of that iron oxide present in the toner powder and use the carbon from that plastics to regenerate that pure iron that you see. So 98% pure iron, and if we can add on that valuable alloying additive of carbon in there, you've pretty much got a nice, useful alloy out of that waste resource. So that type of transformation allows us to come back to this picture again and say, if we start to really look at the various elements that are available to us, the metals that are available to us, the oxides, why can't we start to look at that in a much more favorable manner? So for us, it's been about that whole journey of looking at this whole ecosystem of different industries who want to come together. Of course, it's very important that we continue to have that conversation, as we're doing with our state government, who are indeed looking at how a lot of these types of ideas can be brought to life. But indeed, whether you're a small producer or a large producer, our industry partners, people like Molycop, who are facing that situation right now, which is, how am I going to source materials I need to make my specialty product? Now remember, here's a manufacturer who has got a global presence. The steel that they make is exported across globally. We've got a manufacturer who's got a 100-year proud history of manufacturing fantastic high-quality products right here in Newcastle. Why can't we actually enable that to remain globally competitive? And this is where the science needs to come into pictures. Look at traditional industries and how they can actually be sustained in the long term by looking at high-value materials alongside a lot of the products they make. And at the same time, work with recyclers, people like TES, who want to indeed produce materials like those plastic filaments. So I would basically say that if it weren't for the fact that the confidence that our industry partners have in the science, we wouldn't be commercializing these technologies in Australia. So I do want to give credit and acknowledge and applaud a lot of our industry partners who love the science, because they know they've got to love the science first for the sake of science and supporting innovation and new ideas to flourish and encourage young people to participate in that journey. So for us, that's an important element. When we train our young people in this space, it's important that they start to appreciate the context and the world around them, and they see how their work can actually be such a game changer. And for me, that's in a way the most inspiring thing in looking at how our undergraduate students, our postgraduate students, and all of them get excited about the fact that they could make such a huge difference to the world. And I think, to me, that's what gives us hope, is the fact that there are some brilliant, amazing young people who do this and do it for the love of science, for the love of engineering. And I think, to me, what was best thing I heard from, in fact, colleagues from New South Wales government who were visiting us yesterday, who said, it's so fantastic to see that kind of pure science happening in our universities. And here was somebody who was basically looking at technology and the implementation of technology, but could at the same time appreciate the fact that without that underpinning science, we won't be able to deliver a lot of these new technologies to the world. I want to, of course, leave you with some few thoughts. Our recycling journey is really only started. We want to be able to look at how this can create impact globally, but we want to do it going beyond the 3 R's. The reduce, reuse, recycle is only a part of that journey. The 4th R, which is really around reforming our materials and transforming them into valuable products so that we can ultimately create green materials, is really, really critical. Can we do that through our Microfactories technology platform? Absolutely, yes. We know in looking at how these microfactories are working, both, of course, at UNSW, but also the trials and the work that our industry partners are doing shows us that indeed these are commercially feasible. And indeed, it requires support. It requires all of that science, but it's like any other new technology. In the early days, there will be struggles. There will be questions around what is the scale at which you need to operate, what value you bring economically to the society. But one thing for sure, if we all collectively see this as our collective responsibility and work with communities and businesses and universities, I think it's going to deliver the economic, social, and environmental benefits. And I do want to thank, of course, Chris for having me, and for all of you for basically the opportunity to speak with you. If you are interested in looking at some of the products and more information, that is certainly available for you to have a look at. So thank you very much for having me here this morning. Thank you.
I'd like to invite some questions for Veena. Wonderful talk. Can I maybe ask the first question? Do you see the microfactories, when they're developed and rolled out, would you have a microfactory that specialises in one type of recycling? So you have one microfactory for glass windshields, another one for electronic products, or are they more?
Yeah, no, that very, very good question, Chris, because I think that's really where, we need to be able to look at that infrastructure can be made to be really, really complex if you want to go down that path, or you can actually start to look at modules that do only one or two functions. And I think that really comes down to the ability of an operator to actually set up a larger version of a microfactory that does multiple things, or indeed, if you just want to be able to produce one single type of glass product, then you basically keep that at one low temperature, one module, and let that operate if that's all your operations will allow you to do in terms of capex and the capacity to deliver. But if you are a larger organization and you could also then have higher temperature modules attached to it, you could then start to look at creation of those types of metallic alloys from glass. So you can look at multiple products being generated out of a microfactory, but it really comes down to operationally whether you've got the right modules or not. So absolutely, it's feasible to look at a whole series of modules if you so desired in the long term, but you can always start with limited number of modules to get the ball rolling.
A question, Bruce? Oh, sorry.
Hi, Veena. I'm Tom McCullough from the New South Wales Smart Sensing Network. That's absolutely amazing. It seems as though you've done an absolutely fantastic job at sort of the sexy end of the materials science. Is there still a lot of work to do at the less fashionable end of the process in the collection, the distribution, the sorting? I guess there's threshing and pulverizing and all this sort of stuff. Is there still work to be done there?
You know what? I mean, of course, in Australia, we have been doing a lot of that work up front. Over time, as you know, people, businesses and so on have been doing. And of course, our collection systems and so on, the state governments and councils and so on have got well-established systems that allow you to collect at the front face of it. As we know, councils are responsible for that function. And of course, there are various sort of processors who then move it along that value chain. So I think in a way, the systems that we already have in place in Australia are really advanced, and I think that's fantastic to see. And in fact, that really puts us in a very strong position. Because if you want to be able to source those materials, for example, if there is a materials recycling facility or MRFs as they're called, if you want to be able to source those materials, you can actually talk to various operators and go and find the right kind of resources you want, because the system is really well established and has been running really well. It's the value add bit of it at the end that we, of course, haven't done, because we've been sending away a lot of these types of resources to other parts of the world. So I think, in a way, we're in a really good position to take advantage of the systems that are already there.
Peter?
Yeah, Peter Tyree. Veena, yeah, very good talk, thank you. Perhaps the secret, I'm going to ask you a question on, is the secret to the microfactories 3D printing? Is that, above anything else, going to be the lead?
Oh, it's like asking to choose between your kids, right? Some are better behaved than others, but you still love them all, and I have too. But I guess, and I mean, the short answer, Peter, is that, yes, of course. I mean, some technologies, and the best way to sort of compare and contrast will be that Some processes will operate at lower temperatures. The examples, of course, plastics is a good example there. But, a lot of the metallics that we talk about and the rare earths and so on, they need higher temperature processing. Of course, that's what thermodynamics dictates. So it's not as if, the high temperature processes are problematic. It's really the fact that it is more complex. So if you want to be able to generate and regenerate these types of products, you would really be looking at the complexity, and that's why I was sort of talking about the various modules that allow you to extract out different types of alloys, because even in one complex circuit board, you could potentially make 2 or 3 different types of alloys. So the advantage of having a complex system like this is that if you were to control those varying temperatures, so selectively, if you can assign those transformations to occur and you selectively dissolve out those various elements, you can actually get so much more value out of these types of range of different types of complex alloys. And of course, then the ceramics at the high end of the spectrum. But absolutely, the complexity lies in temperature, the processing conditions, and how these modules are engineered and designed. So part of the work that we are doing at UNSW is also in the patented technologies is around how we can then design these furnaces, and in fact talking to really specialty manufacturers right here in New South Wales who are able to make these systems for us, which is the other fantastic thing, that we've got the capacity to manufacture some of these really complex systems, which is what we're doing.
Hi, it's Stefan Wagner. Great presentation, Veena.
Thank you.
My wife and I often complain about the attitudes we have towards, and you sort of alluded to it, the disposability of so many things, and we massive landfill problem that we have at the moment. So we know that's a big problem. So there's 2 other challenges. There's one that we have this buyer behaviour at a consumer level where we want things cheap and cheap and cheap, and you alluded to that. It has to be affordable. How could you possibly, and this is where the question comes in, how could we influence potentially, without introducing massive regulation, I know that's happening a little bit in Europe, to make sure that when these great innovators at university are developing new products, how they also make sure that they consider this entire cradle-to-grave process. So, you're trying to extract at the end efficiently and effectively. How do we make sure when we hold the manufacturers to account and the new innovations they're popping out, so they take into account the extraction process as well as how we can more efficiently take advantage of all of this and remove ourselves from this cheap. So you can understand it's a 2-part question, but it's complex. I understand that.
And look, that is spot on in terms of us actually asking the big picture question. And the big picture question is that we really should not be looking at materials if all they're going to do is they're going to be a little piece of, let's use the absolute basic, the little plastic straws or the little sort of toys that last you for 5 minutes, or the little, piece of clothing that you might have worn once or twice. So I think to me that is a holistic question around, are there industry associations that are taking responsibility also for action? So I do understand, businesses want to sell more and so on, but we can afford to look at it from the context of let us create products that will last the distance, that are not seen as, the fashionable thing to do, that we change around every time a new season or a new sort of marketing design comes on. Let's start to think about how products can actually be modular in nature. So if we want to be able to refurbish and repurpose and refit, that should be part of our economy as well. And that actually goes down really well to one of the points I was making, is about making parts and components. If you actually start to create those parts and components, you can imagine in your car, if you were to go off to your auto mechanic to fix things, instead of hearing the fact that, well, I'm going to have to wait for 2 months before that part comes from Japan or wherever, we actually should be regenerating a lot of those parts, spare parts, components, and so on a small scale right here, so that it creates also that cultural shift, that every time I've got to go off and buy a new phone or a new computer, but rather let's just see, is there an opportunity to enable us to also think of the life of that product as a whole and look at that as part of the culture. Because, I mean, in a way, if we keep thinking about stuff being really cheap, and of course, producers have to take some responsibility too. I mean, you alluded to Europe. Definitely that is the case. We're starting a partnership now with Planet Arc, where they're looking at producer responsibilities as well, because there's so many different types of products that just simply, yes, the big things like the tires and so on, there's Tire Stewardship Australia, which is fantastic. So that's an example where there's a body that's been set up to recognize that, we need to have, businesses participating in those schemes. So I think that's great. But what happens to all of these other consumer products? Clothing is a good example. So, and of course, electronic devices as well. So I think in all of these, if there are industry bodies that come together and collectively work with government or set themselves up as independent bodies, I think we can actually enable that awareness and education piece along with influencing consumer habits. And of course, there are lots and lots of, sort of work being done. Media has, of course, done a fabulous job in terms of highlighting some of these issues. So I think we need to be able to see all of that in a positive way. And of course, to top it off now, all of this sort of new guidelines from China is going to ask us that question even more so.
I think we've got time for one more question.
Just one thing you haven't mentioned at all is the waste from your microfactories. And I'm thinking you're still running high temperature furnaces and you're going to have gaseous waste and you're going to have microfactories embedded in the community more. What are the issues of those? Because you've still got some rather noxious things in your gaseous waste, presumably.
So indeed, maybe just the first point there, that the gases actually are not noxious. And so at high temperatures, when you talk about, metals manufacturing technologies, what you've actually done, and that's why I was sort of making the point between high and low temperature. If you know that you're operating in the zone where you will be generating noxious gases, you actually do not want to work where these types of gases are stable and are being generated. What you want to do is either you push the temperatures up to well beyond 1,000 and 1,100 degrees Celsius. So part of our design in the way we look at, so I was talking earlier about modular design, is to be able to create separate modules that allow you to operate in the high temperature zone if that's what your input feedstock has. So if you've got waste plastics coming in with your electronic waste, like I was talking about the metallics, what we're doing is when we push the temperatures up to 1,100 degrees Celsius, you've actually broken down those long chain molecules and you've actually created separate structures and molecules of carbon, for example, or silicon carbide if you've got some amount of glass and plastics left over. So that's the reason why I was referring to what happens at high enough temperature, that you actually don't liberate them out as gases. What you do is you regenerate them into solid forms. And that's really where a lot of the science that we've done has shown for the first time that you can indeed achieve those outcomes. But to do that, then you have to go to a whole different temperature zone. And that's why, if you're not able to operate a module that is as complex, which is why I was making the point earlier, is that it depends on your capacity to operate different types of modules. Then you want to stick to the lower temperature end where you do not generate those gases. So it's really around being very careful in how you take the scientific knowledge. And that's why, of course, the technology has to be patent protected. You don't want, people just going off and doing whatever they want. It's got to be done in a proper systematic way where you do control and have process controls in place to be able to create value-added products in a safe and a sustainable manner. Oh my gosh, it's very generous of you.
Thanks so much.
Thank you so much, Chris. Appreciate it.
Thank you, everyone. Thanks so much. Our next speaker on the 15th of August is Chief Cancer Officer of New South Wales and the CEO of the New South Wales Cancer Institute, Professor David Currow, talking about how cancer outcomes can continue to improve. So thanks again, everyone, and particularly to Veena, our wonderful speaker today. Thank you. Have a good day.